get to continue with antiderivatives today. Yay! The third component of calculus. So we're training our minds to think backwards now, and we're learning some tricks. And so yesterday, after we kind of got the big idea in, we just did a lot of like practice problems. And it's just one of those like where you just want to get very proficient at it, where you can just kind of think through it fast. Just like now, if I asked you what's the derivative of 4x to the fifth, you could do that really fast now. So this is just one of those things we want to be able to get good and fast at that. So today we'll start with just a couple more examples of thinking of antiderivatives, and then I'm going to tweak it a little bit and ask you a different type of question. But I still want to show you like some just examples of all these antiderivatives and getting into that. So we talked about notation, all of that yesterday. We've been doing practice problems. So I'm going to jump in today. Our first one that we're just going to practice with is we're going to do x plus 2 dx. And this is going to use our rules, but it's going to be another rule added in. This is also going to incorporate the sum or difference rule, just like everything else we've done this year. We just look at each of them separately. So if I asked you to derive 5x to the 6th plus 2x squared, you just derive both of them on their own and then attach them. Same thing with antiderivatives. We're going to antiderive each of them separately and just attach them. And so let's think through our rules that we talked about yesterday. When we use our power rule now, we add 1 to the power and we divide by the power. For x, that's going to give us x squared over 2 plus, and then when we antiderive 2, that'll be 2x. And then because this represents a whole family of options for all of our antiderivatives, we've got to put that plus c. And it could be any constant then. So sum or difference, same as all year. We just treat them each on their own. Okay, let me give you one to kind of look at, and I might give you one to try after this. Let me give us this. We'll do this one together. 3x to the 4th minus 5x squared plus x dx. We're going to do this one together again, kind of practice, get our minds kind of all warmed up. Then I'll give you one to try. Separately, 3 different problems. For the first part of that, add 1 to the power, divide by the power. Second part, add 1 to the power, divide by that power. And remember that constant in the front, it just tags along. And then third one, add 1 to the power, divide by the power. And then we're going to have plus c. And again, what's nice about these is you could just derive your answer and see if you get back to the original, so you'll know if you're doing well. Okay, let me give you a little string to try. Let's do try to antiderive that or integrate it. It's another word for it. And then we'll check our answers. Anybody make it just 7x squared? Or did you leave it the 14 over 2? You simplified, so we could simplify if we want to. 7x squared minus, we could simplify that to x cubed plus 628x plus c. Are we anti-deriving well? Yay. This is one of those things where you like, party trick. You like take this to somebody and you're like, I can solve this. And the squiggle is just like, wow. They want to know if you're right. Yeah, but I mean that you could know what the squiggle means. Yeah, like this is right. I know it's right. Look at the squiggle. The squiggle tells me what to do. All right, a couple other ones I'm going to show you about just so we're thinking through this one. This next one's kind of strange, and it's if we see this. No integrand, so just the bookends, the squiggle and the dx. Well, kind of like with all of math, if there's nothing there, it's an understood placeholder. So then technically there's a 1 there if you don't see it. So if they just have the squiggle and the dx, there's a 1. And then if we integrate 1, it's an x plus c. Okay, then I want to show you this one, just some things to be careful of. We have something like this. Yesterday we talked about we can't do the power rule until that variable is in the numerator. However, mathematically that 2 needs to stay in the denominator. So I'm going to rewrite this, and when I rewrite it, I'm going to leave my 1/2 and then just bump up the x cubed. So it'll be 1/2 x to the -3rd. Leave the 2 in the denominator. And then when we go to integrate, that 1/2 tags along. Add 1 to the power. Divide by that power. Plus c. And then they always want us to fix our negative exponents with those x's. And so I'll end up getting 1 over -4x squared plus c. There's our antiderivative, or our integral. Okay, next one I want to show you looks like this. It will be the integral of x plus 1 times 3x minus 2 dx. Okay, there's good news and bad news with this one. Which news do you want first? The bad news is. The bad news is there is no form of product rule when we antiderive. The good news is there's no product rule you have to memorize when you antiderive. So when we have a product, we have to manipulate it in some other way where we don't have a product anymore. What could we do with this one? We could FOIL, and that's what we're going to have to do because there is no product rule. So that'll give us 3x squared minus 2x plus 3x minus 2. And then when we FOIL, the product is gone, and now we just have sum or difference, and we can integrate all of those pieces. And when we integrate, we'll get x cubed plus x squared over 2 minus 2x plus c. Who out there thinks they will be the person that forgets their plus c? Anybody seeing that for themselves? A couple yeses. Somebody's got to remind you. Plus c. Okay, now, yes. Over 3. Anything else right there? Okay, next one I'm going to show you. This one. X plus 1 over the square root of x dx. Kind of a good news, bad news situation again. No quotient rule, so we don't have to memorize a quotient rule, but we have to always then manipulate it in some way to get rid of the quotient rule. Now for this, there are two methods, and it's really just a preference of what you like better. I'm going to show you both, and then from here on out, you can decide what you want to do. First method is we could make separate fractions. So I could make this x over the square root of x plus 1 over the square root of x. So it's kind of like they were smushed together and we're separating them with their common denominators. And then from this point, once I make my separate fractions, I want to simplify this a little bit more. So thinking back to algebra, if this is x to the first power and this is x to the 1/2 power, when you divide, you're actually subtracting their powers. So this is x to the 1/2 plus this one, I need to bump it up. It'll be x to the negative 1/2. And then I've got a sum or difference that I can do. With my sum or difference, add 1 to the power, divide by that power. But remember, instead of dividing by 3/2, we're going to multiply by 2/3. Plus, okay, then for x to the negative 1/2, add 1 to the power, divide by that power, which is the same as multiplying by 2, plus c. Okay, so we're going to make sure we're okay with everything in the red because we did a lot of little manipulations, and then I'll show you the other method. So everything making sense? Yeah.
Very first step to the very second step. So when we have the two square roots of x in the denominator, so like for the first one, is that equivalent to x over x to the negative 1/2 or just x over x to the 1/2?
X over x to the 1/2.
And the same for the other one, would be 1 over x to the 1/2?
Yes. From here to here? Okay, so if we have this, let's think back to this in Algebra 1. We would have done 8 minus 5 to get 3. So 1 minus 1/2. Yep. What else on this part in red? Okay, so that's, yeah, Max. Here. Okay, so from here to here, that makes sense? So what we do is back like in Algebra 1 when you had exponents, you do top minus bottom. So 1 minus 1/2 is x to the 1/2. Okay. What else there? Okay, method 1. Method 2, we can take that binomial on the top and keep it, so the x plus 1, and we can bump up that square root of x, but when we bump it up, it's got to now have a negative exponent, and then we need to distribute that through because there's still not a product rule. When we distribute it through, x times x to the negative 1/2. Now, algebra rules again with exponents. When you're multiplying, you add their powers. So 1 plus a negative 1/2 is x to the 1/2 plus 1 times x to the negative 1/2 is x to the negative 1/2 dx. And then you'll see we're at the same spot we were with the red now, and we would go through and do power rule just like that one. So it's really like the red is you're using your division properties with exponents. The green, you're using your multiplication properties with exponents. They're the same amount of steps. It's just however you feel like you would do best. They'll both get you the right answer. But that's how we do division when we don't have a quotient rule. Okay, anything, red or green up there that you want to ask a question on? Okay, what if I said our next one deals with Pre-Calc Chapter 5? Let's do some trig identities. All right, so let's try this one. The integral of the sine of x over cosine squared x dx. All right, now again, there's no quotient rule. So all of that stuff you practiced with all of your trig identities last year, it was so we could manipulate. Do you remember the section where you had two trig things and you had to like manipulate them till they both were equal? We're trying to get this to be something that we can derive. So we're trying to rewrite this in a way that we can use it. Well, one of the first things that you would have tried last year is you would have written it all in terms of sine and cosine. It's already there. So now I'm going to try this. I'm going to separate that cosine squared and make it look like this. We kind of did things like this back when we were learning how to derive these. Now we're working backwards. Bless you. And again, in my mind, because I've been doing this for a while, I want to get rid of the quotient because I know that there's no quotient rule with anti-deriving, so I'm trying to get rid of fractions. So how could I rewrite sine over cosine? Tangent. And how could I rewrite 1 over cosine? Okay, now this will test your memory. That is a derivative of something. 1 of the 6. Secant. So that is secant of x. And then it still could have a constant on the end, so we still need to put that plus c. Okay, so what about a little brief commercial and we talk about all those 6 trigs and their derivatives? Would that be helpful right now to try to remember those? What is the derivative of sine of x? Cosine. What's the derivative of cosine? Yes. What is the derivative of tangent? Good. What is the derivative of cotangent? Good. What is the derivative of secant? Good. And because of just multiplication rules, like those can be flipped, like we saw right here. And then finally, what is the derivative of cosecant of x? Good. So now we're going to try to get it in these forms so that we can go backwards to its antiderivative. So still sticking around. All right, we're getting ready. I told you I've got a little tweak for you. So that's what's next. So right now where we're at, we've just been like looking at all kinds of ways we can anti-derive and go backwards. Anything right here at this point you're thinking conceptually or just like algebraically, any questions you can think of before we tweak this a bit? Okay. Okay. Dx. They would have to put 2 in there. So they will only do, let me see if I'm asking you right. Oh, when the derivative is 0? Yes, they would put 0. They only use the emptiness for a 1. Yeah. Yep, good question. Mhm. Mhm. Anything else we can think of right now? Yeah. To put something in its what? Right. So integrating is we're going to take all this data and we're going to be able to put it into an area formula is what this is actually, its application is going to be. So we're taking a bunch of like data and growth data and we're going to be able to like, it's called an accumulation function eventually we'll get to, but we are taking growth patterns and figuring out how that tells us the amount of something. Now, integrate itself, like as a verb, I don't know if it's got much. I mean, I'd have to see like why that verb is chosen, but like it's a bunch of data that's actually going on in the real life. They're taking a bunch of data and integrating it to find amounts. That doesn't answer it well. I mean, I'll look that up better, but yeah. That's not the connection. Like Max was looking that up too, but it's different than that. Um, it's gonna be more along the lines of the pizza video that we watched. Like we're gonna have the curve of that pizza and that the rate that pizza was changing between rectangles, and we're gonna be able to use integration to find that area of that pizza. But it's a big process. That's why we all are on this chapter 4. But 4.2 is called area because we're going to get into the concept of it and the history of it and that kind of thing. But like the problems that it'll lead into, like by the time we get to the AP test, like problems they've asked on the past are like, if people are going to a concert and 10 people per minute get into the door for the first 5 minutes, and then 15 people per minute get in the door the next 15 minutes. What's the amount of people that enter through the door? And we can take growth rates and use antiderivatives and integrals to figure amounts that are happening, which a derivative is a growth. So, but that's what we're kind of getting into with all that. It's pretty cool overall. Other questions? All right, next topic then. We're going to find a particular solution. So what that means is we're going to have some more info given to us and we're going to be able to figure out what C is. So let's start with this question. We're going to do f prime of x, but it's a capital F, equals 1 over x squared. And big F of 1 equals 0. Find big F of x. Okay, then before we get into like any of the computation, we just want to kind of look at how they have things noted. Everything has a big F. So across the board, that's the same. So because everything has a big F, now we'll look at symbols. This has to represent the derivative. And then everything with just the capital F has to represent the original. And here's what they're giving us. They're giving us the derivative, and they're giving us a point on the original. And that's going to help us find what the original is. let me kind of describe this with a picture. And it's not necessarily with this example, but just to kind of help us figure that out. Actually, no, I'm going to save the picture for the second one. I think it'll work better on the second one. We'll just talk about the math on this one. So what we're going to do, if we have the derivative, we're going to start by integrating this. We want to take the derivative and go backwards. And so we'll make our own little problem, our squiggle, 1 over x squared dx. And then we're going to do what we've just been practicing yesterday and today. We're going to integrate. I love this stuff. No, it's not. I think they're liking it just fine.
By looking at their faces, I can hear.
Someone help me out here. Someone help me out. Show Mr. Short how much you... Okay. It's not interesting yet. Once we get the history of it. The history comes in 4-2. It's really cool. There's a couple wow moments. Over this one, not that I know of. Like mathematicians would duel it out and kill each other over their ideas.
They would fight for their titles.
Mm-hmm.
They would try and create problems that the other couldn't solve.
They would actually have duels. They're like, well, I don't believe in your hypothesis, so we will duel it out at noon.
Like actually.
Yes. See, Mr. Short, he doesn't get it. All right, so now when we do power rule, add 1 to the power, divide by the power, plus c. I'm going to rewrite that. I'm going to put the negative on top just because I think it looks better. Negative 1 over x plus c. Okay, are we okay with everything in green so far? This answer is our general solution, and I'm going to put it equals capital F of x. So general solution for our antiderivative. Now I'm going to take this general solution and I'm going to plug in this point that I know happens on this graph. And so the 1 is my x, and the 0 is what it equals, or you can think of it as your y. If I place those in here, it will be negative 1 over 1 plus c equals 0. Then I can add 1 over c equals 1. So then this antiderivative at that specific point, my particular solution for capital F of x is going to be negative 1 over x plus 1. That's my specific c value that makes this work. So that's how we're going to get a particular solution. We'll need the derivative and information about the original. Okay, let's try another one of these. Let's do, I'm going to write it a little bit differently. dy dx equals 2x, and we have the coordinate negative 2, negative 2 on y, so on our original. So we have our derivative. We're going to work backwards to find our original, and then we have a point that's on the original. Okay, we will integrate our derivative. So the integral of 2x dx, what is that antiderivative? X squared. And we'll put our plus c. So this is our original. So this is what y equals. equals. Okay, we're going to take that general solution and we are going to plug in this point. So for x, we're going to plug in a -2, and for y, we're going to plug in a -2. So we've got a c that is going to equal -6. And so then our particular solution, y equals x squared minus 6. Okay, so here's what's going on. Visually what we're doing. When we have our derivative is 2x and we go backwards, x squared plus c, what does the graph of x squared look like? Parabola. The plus c, so if you think about all the options it could be, x squared plus 1, x squared minus 5, x squared plus 10, it's a whole family of answers. And so it could look like this. It could look like this. It could look like this. All of those. This isn't great, but we see all these parabolas. We get the idea. So this is all of the options to infinity of what that could be. This is telling us, hey, our answer has the point -2 to -2. So it has to be that graph. We're finding which one it has to be. When we know our antiderivative and we know a point, we know which one of the family it is. And then we can find that out. Okay, questions there. All right, let's try another one. But this time I'm going to get a second derivative in the mix. So I'm going to put f double prime of x equals 2. F prime of 2 equals 5. F of 2 equals 10. Okay, now f prime of x. So this is our only one that's actually a function. The other two are sets of points because they have a number here. We know our second derivative function. We know a point that's on our first derivative, and we know a point that's on our original. So what we're going to do is we're going to integrate second derivative to get to our first derivative. And then we're going to solve for c. Then we're going to integrate first derivative, go back to our original, solve for c. So it's the same process, but twice. So our second derivative is the equation of 2. So we're going to integrate 2. That goes back to 2x plus c. This was second, and we go backwards. That's going to equal our first derivative. This is our general solution of the first derivative. Now we're going to figure out the particular solution of our first derivative. So what we know is that x is 2, the derivative equals 5. We're going to plug those numbers in. 2 times 2 plus c equals 5. That means c equals 1. Making our first derivative 2x plus 1. Now that we know first derivative, we're going to integrate that to get back to the original. Integrate 2x plus 1 dx. 2x is going to go back to 2x squared over 2. So that's the same as x squared plus x plus c. And that takes us back to our original, so that equals f of x. So for this, we're going to plug in the information we know about the original. X is 2, and it's going to equal 10. So c equals 4. So then f of x equals x squared plus x plus 4. And there's our particular solution for the original graph. How are we doing? Okay. Are we getting faster at finding our antiderivatives as we've been doing this more and more? All right, yeah, we've got time for this last one. Last one of the day, and then we'll do more tomorrow. Last one of the day is going to be this situation, but with trig. Let's have f double prime of x equals the sine of x. F prime of 0 equals 1. F of 0 equals 6. We're going to start with second derivative, integrate, solve for c, integrate, solve for c. All right, so we're going to start by integrating sine of x. So if you wrote down all that stuff, go backwards. What is our, and then you could also think about that little chain we made yesterday. What's our antiderivative of sine of x? Negative cosine, good. So we'll have negative cosine x plus c. This takes us back to first derivative. Okay, what we know about first derivative, x is 0, it equals 1. So negative cosine of 0 plus c equals 1. I'm not answering that. We're just letting that go. He's going to talk forever. He's All right, cosine of 0. What's cosine of 0 on the unit circle? 1. So this is going to be a negative 1. So c equals 2. That makes our first derivative, our particular solution, negative cosine of x plus 2. Okay, now we're going to integrate that. Negative cosine x plus 2 dx. What's the antiderivative of negative cosine? Negative sine. So negative sine x plus 2x plus c. And that equals f of x. Okay, now for our original, what we know, f of 0 equals 6. We'll plug a 0 in for our x's. Equals 6. Okay, unit circle, what's sine of 0? 0. So c is just going to equal 6. Then we get f of x equals negative sine x plus 2x plus 6. And there's our final answer. All right, we are at a good spot. Leads us into word problems tomorrow for a Friday. Practice this stuff. Any final questions we want to ask or get out of the way before we are done? All right.